I want to talk to you briefly about solutions. A lot of what we're going to be doing in the water unit deals with having a good understanding of what happens when something either does or does not dissolve in water. So I thought it'd be helpful to go over some things that we've talked about. One of the most familiar ideas that we've talked about is this idea of substances being soluble or insoluble. A key example of something that is soluble is table salt. Table salt has the chemical formula NaCl. And remember that table salt is an example of an ionic compound. Ionic compounds are typically composed of ions, and most of the time that means you've got a metal species and then a nonmetal. In this case, sodium is a metal, chlorine is a nonmetal. Remember some unique characteristics about soluble ionic compounds. Soluble ionic compounds in water will dissolve, and when they dissolve, they do something unique. They form individual ions. For example, you see the green chloride ions and the red sodium ions. You might also notice that in this diagram we see some solid, and this solid shows the characteristic crystal structure of ionic compounds. Unlike covalent compounds, ionic compounds form this crystalline structure. Covalent compounds, on the other hand, do not form this lattice of ions, because covalent compounds are not composed of ions, they're composed of molecules. Another thing that you're going to be seeing that's a bit different in this unit is we're going to start expressing how concentrated a solution is. And you can imagine if we took two beakers, and let's say for the sake of the argument that they're identical, even if my drawings aren't perfectly identical. And let's say that we put the same amount of water in each. And then let's say we add something that dissolves. Let's say that we add 1 spoonful of salt in the first beaker and 2 spoonfuls of salt in the second beaker. Now we stir it, and we know that over time we would stir both of them, and they would both dissolve. And when they dissolve, they appear to our eyes like they're identical. The volume hasn't really changed much, and the substance that was once solid has now dissolved. And remember that really what's happening when it's dissolving on the nanoscale is the solid crystal lattice is being broken apart because water molecules are attracting to the individual ions. So water molecules will come in and attract to either the sodium ions or the chloride ions. Remember, water has different parts of it that are positive and negatively charged, so it's going to attract differently to different ions. We need a way as chemists to take a look at this scenario and describe them quantitatively, and there's a number of ways that we do that. One way is by expressing something in terms of parts per million. Now, parts per million, for our sake, is equivalent to a concentration in terms of milligrams per liter. And what that means to us is the milligrams refers to the solute. The solute is a substance that's dissolved. So in the example I was given before, it's the green solid here. And the volume of the liquid is what we're referring to in liters. So one key way that you'll hear us refer to how concentrated something is parts per million. Typically we use parts per million when we're dealing with contaminants that are harmful to the human body, because those are typically things that are bad for us, even in very small concentrations. Now if we deal with a situation where it's more concentrated, then parts per million really becomes less useful to us. So what we tend to use in that case is a new method of concentration. And the one that you're going to see most frequently is something called molarity. Now molarity is symbolized by capital M, and we calculate it by taking the number of moles of solute divided by the volume of solution. So once again, in order to know the molarity of something, you need to know the number of moles of the solute, and then you need to know the volume of the solution. Sorry about that. And that volume should be in liters. So molarity has the unit of moles per liter. Now you may have seen this in experiments and not even thought about it, but every time that you pull a bottle of a dissolved solution that you use in a lab, it's often labeled with this capital M. Most recently in AC1, the gas group used a bottle of 1.0 molar H2SO4. And what that tells us is that there is 1 mole of H2SO4 dissolved in 1 liter of solution. Now, even if you don't have a whole liter, this concentration still remains the same because that's the ratio. The proportion is 1 mole of H2SO4 per 1 liter of solution. So those are some brief overviews. What might be helpful for you as you look forward is to start to think about how you're going to go about doing these calculations if we have to convert between parts per million and molarity, because you will be asked to do that in the future. But I'll follow up with another screencast going through some examples of that. So just use this screencast as an overview to expose you to these new ideas of concentration, which are parts per million and molarity.